All right, so I'm here. Um, we have about 5 minutes before class starts. So if I can answer any questions. That would be great. It would be a good use of these 5 minutes. So go ahead and ask questions before class, and then once we start the class, we'll focus on the topic of today's lecture. I have talked to some of my colleagues about what tool they are using to teach classes online, especially those who used to teach face-to-face classes like myself. And many of the other professors are using Zoom because apparently Zoom is the district has some kind of a deal with Zoom, and so everybody is using Zoom. Jose is asking about exam 2. I think in the previous class on last Thursday, we talked about it a little bit. So I still haven't really quite decided yet. It kind of depends on what type of equipment people have, and I cannot rely on the equipment that not everybody has. So I gotta keep that in mind. Um, so that's a very good question, Jose. I just don't know yet. And by the way, you can now go ahead and remove your easy YT prefix because the other Jose is gone.
Sure. So,
Hi Hugh, I can hear you.
uh, I'm looking ahead. What is that? Is that pi? Are we talking about counting today, right?
Uh,
The module?
we are gonna work on call. We are done with
Uh,
calling and returning from subroutine, and so we're gonna work with returning a scalar and also parameters and local variables today. So those are the modules for today. And let me see if those links work or not because I remember that some of the links do not work because it links to the wrong URL. Nope, this one is fine. So I think I might have fixed the links already. Let me try the other one too. And this one is not working because I can see the URL is wrong. So let me go ahead and fix that. So the way you fix the URL in case you run into this problem is to change the first part of the URL to https:// power.arc.los3os.edu/ And this is the most important part. Starts with a tilde sign and an AUYEUNT, and that is the new home for the nodes. So let's try that again. Okay. Yep, that works now. Okay, very good. So I'm gonna close these first. Okay. And then go back on this one, get rid of this one, get rid of that, and get rid of that. Okay. All right. We still got a little bit of time before class starts. Nope, I don't have that time anymore. It is exactly 5:30, so I'm gonna get started. All right. So what we'll do today is we are continuing from the lecture last time, which is calling and returning from subroutines. And what we'll do today is to move on to returning a scalar and also how to use parameters and how do we use local variables, like the way we usually do in the C++ program. So that's going to be the focus of today's lecture. Um, so let's go ahead and open this one up first. Okay, so we'll look at returning a scalar value. This is one of the shortest modules ever in all of the modules that I have written. You can see that this is it. Not too long, huh? All right, so let's just go ahead and take a look at the content here. In general, most compilers for most architectures pick a register to store the scalar return value of a subroutine. So the question here is, what exactly is scalar? Scalar means the return value, the type of the return value, is something that is quote unquote relatively small. Okay, so I have to emphasize on relatively. Depending on your architecture, if you have a 64-bit architecture, a unsigned or signed 64-bit integer is a scalar. If you look at a double, it is also a scalar. A char is a scalar. A pointer is a scalar. A structure is not a scalar. Okay, so the only type of return value that is not a scalar in C or C++ is a structure. Then what about arrays? Well, guess what? You cannot return arrays in C or C++. So we don't have a concern about returning an array. You can return a pointer. You can return the beginning part of an array, but you cannot return an array in C or C++. So we don't have that issue. Um, Garrett is reminding me about the YouTube stream. Thank you. And I believe the YouTube stream is working because I have one browser opened on the YouTube stream, so I think it is recording. Yep. Thank you. All right. So on the processor that we are using, I am going to choose register A. So register A is what we use in this class to return a scalar return type from a subroutine. So if you have a C code that looks like this, okay, obviously not very useful, but it serves the purpose of illustrating the point that I need to make. So if you have a C subroutine that returns an integer and the integer is returning is 5, then what we do in assembly code to implement this particular subroutine is to use 5 as a start label of the subroutine because that's the entry point of the subroutine, and then return 5 as a statement is kind of tricky because the return value of 5 is taken care of using this particular instruction. All we need to do is to do a LDI a comma 5, which loads a constant of 5 into register A. And that's it, because register A is interpreted by the caller as where the return value is going to be in. Okay, so this is all about an agreement between the caller and the callee. The next three instructions are things that we have already talked about in the previous class. LDBD is based on the assumption that the caller has already pushed the return address on the stack before doing a JMPI to this particular subroutine. But once we retrieve the return address from the stack, we are incrementing D because that location on the stack is no longer of any use anymore. We have just quote unquote consumed it. And I got next question. Let me finish this part first, and then I will address next question. Um, and because B is now loaded with the return address, a JMP without the I, a JMP B instruction, is going to go to the place that register B is pointing to. So I'm going to read next question now. Does this mean we always assume register A as our return value, much like we always assume the last element of RAM is the top of our stack? Um, the answer is yes. So the caller makes that assumption. If the caller is calling a subroutine and the subroutine has a return value, the caller would look for that return value in register A. Is that okay or not? All right, cool. So even though this is a really short module, we're going to write a sample program to illustrate the point of this particular module. And I think I can recycle one of my mouse pads. Let me see, do I have one that is still open? Nope. Okay, that's fine. I can always just go ahead and make a new one. Mm, I'm thinking, whether to use a command line interface or not, because that way I can actually also show you guys, um, the code once we translate that into assembly code. So I'm going to do it that way, I think. All right. So let me drag the command line interface into view and make it maybe just one stop bigger. There we go. So we're going to go take a look at a program called 7, okay, as a C program. Um, and 7 is not going to do much. All it's going to do is to say 5, okay, int 5, and all 5 is going to do, oops, is to return a value of 5. And then we have a subroutine called 2, and all it does, and you probably guessed it already, is to return a value of 2. There we go. And now we're going to implement 7. And what 7 is going to do, guess what? It's just going to return a value of 7. But it is not going to return a literal 7. It's going to return the return value of 5 plus the return value of 2. Okay, that's supposed to be a plus. There we go. All right. And main can call 7. Okay, it doesn't really matter because, okay, there we go. And return 0 right there. So this is actually a valid program. Okay, this program is okay, even though 7 has a return value. In C or C++, it doesn't really care whether you make use of the return value or not, which can lead to a lot of problems, but in this particular case, it's not a problem. All right, so now the question is, how do we implement this in assembly code? Okay, that becomes the question. So the first thing we want to do is to move things around a little bit. We're going to move main all the way to the beginning, because in assembly language programming, the entry point of starting execution is location 0. So either that, or we can put a JMPI instruction all the way back here to main. So either way works. I suppose I can work with the second way just to illustrate a different way to do the same thing. So the first thing we need to do is to comment out every single line. And since I'm using VI, I can now specify begin every single line with a slash. Let's see, replace the beginning with slash slash and a space, and apply that to all the lines. There we go. So I just commented out all the lines, which means now I can actually specify assembly code interleaved with the comments that used to be C code. So the first thing we need to do is to specify a no-op instruction. The no-op instruction is needed because I intend to use the trace analyzer, and the only way to make use of the trace analyzer is to run the program using the command line mode of Logisim, and in order to do that, the no-op instruction is necessary. Yes, I can display the line numbers. There we go. And then the other thing we need to do is to do a JMPI to main right away, because I'm going to write main all the way down here. Am I muting myself? I don't think so. Hmm. All right. So at least the good thing is it's all getting recorded on YouTube. So even if you have some technical difficulties right now, you can still kind of listen to the recorded version later on. Hmm, that's interesting. All right, all right. So you're not going to miss out much, because I'm just gonna call mains right here, and then what we'll do is we need to call 7 at this point. So to call 7, okay, if you remember from last time and also from the lab from last time, we have to push the return address first, and then we do a JMPI to 7, and that's how we call a subroutine. So typically what we do, okay, I'm going to use the old way and then we'll switch over to the new way after this a little bit. Okay, so we load um, main 7 continuation label, okay, and I have to load it into register. So let's specify register A. And now we need to push it on the stack. So we have a decrement D to allocate a byte on the stack. And before that, it is always a good idea to initialize the stack pointer because main is the entry point of everything. So you can do it at the beginning. In other words, you can go back all the way back to here and then do LDI D with 0. But you can also do it in main because it doesn't really make that much of a difference when you're programming in assembly. Okay, so assuming the stack is already, or the stack pointer is initialized, we just decrement D and then we store in D whatever A has, and then we do a JMPI to the subroutine that we are calling, which is 7. And when we come back, okay, we are going to come back to hopefully this label called main underscore 7 underscore cont, which stands for continuation. So this is a continuation point of after we call 7 in main. And then return 0, just translates to a single halt instruction because that's the end of this program. Unlike in a operating system where when a program is done, it can always return to the command prompt or the GUI. In the toy processor, there's nothing to return to, so a halt instruction typically marks the end of a particular program. Okay, so this is the usual way of doing things, but there's a different way of doing it now. Now, first of all, let me show you these two instructions on line 23 and line 24. Their order can interchange and it will still work fine because one is decrementing D and the other one is loading a constant into register A. So the ordering of these two instructions really do not really matter. So I'm going to make the assumption that we're going to decrement D first and then we do LDIA of some register with the return address and then we store it on the stack. Okay, so now what we'll do is to say, well, this works. But there's a problem with this kind of approach because with this approach, every single time you have a call to a subroutine, you have to define the label for where it is supposed to return. And if you use the wrong label because you copy and paste, the assembler is not going to help you. It cannot help you detect that problem. So it works, but it's not really the best way to do it. So instead of doing this from here on, we can now do something that the new version of the assembler, the one that can do postfix notation, only that one can do this. Okay, so we can now say dot 5 plus and now get rid of this label over here. Now, maybe I shouldn't get rid of it. I should just, oh, I can put it here. Main underscore, what was it again? 7 underscore cont. Okay, so we'll go ahead and keep it here. So now the question is, what is dot 5 plus? Dot is the address of the instruction of the same line as the dot. Okay, so in this case, line 24 is, so we're talking about line 24. So this dot over here, I probably should change my cursor, but we'll do it later. So on this line, on line 24, the dot is referring to the address of the LDI instruction. The LDI instruction has 2 bytes, so the dot is referring to the first byte of the LDI instruction. Now, because it's in postfix notation, so dot 5 plus is literally saying, okay, first we have the address of the LDI instruction of line 24, then we have a literal constant of 5, and then the plus means, okay, just add those two together and give me a new number, which is the sum of the address of the LDI instruction on line 24 and 5. Literally, it's really just saying where the LDI instruction is plus 5, okay, if you want to use the infix notation. So why do we want to add 5? Okay, that's the question. The reason why we're adding 5 is because the LDI instruction on line 24 takes up 2 bytes. The instruction on line 25 takes up 1 byte. The instruction on line 26 also takes up 2 bytes. So now you have 2 plus 1 plus 2. So that means dot 5 plus on line 24 really should be the same as the definition of the label main 7 cont. Okay, we got a question. LDI is 2 bytes, SD is 1 byte, JMPI is 2 bytes. So we need to go 5 bytes past the beginning of the LDI instruction. That is correct, Nick. All right. But you guys remember what I say about taking my words for something, right? So let's not do that. Okay, we'll go ahead and um, run this code, and I just want the minimal at this point to make it compile, just make it assemble. So I'm just make a 7 over here and not even bother to give it any instruction because I'm not going to run this code. It's not going to work. But I do want to find out whether this dot 5 plus turns out to be the same as main 7 cont. Okay, so that's the first thing I want to check is, well, does it actually work? All right. So there's a reason why I do not use. There's another way to do it, but I cannot remember. But VI doesn't paste well into the browser. So mousepad, is better. There's another way. There's a program specifically to put a text file into the clipboard, but I cannot remember the program. I have already installed it, but I just don't remember the name of that program. So now we're gonna go back to mousepad because this is the only way that I can do a Control A, Control C, and then we switch back to the browser and go to the assembler. So I got the processor folder already opened, and we just need to go to the assembler with postfix notation. Go to the source tab right here. Remove all the content of just column A, and then single click on the first cell and then Control V to paste the program. Okay, so everything checks out, and then we switch to the assemble tab because the program is not going to run. I'm not going to load it into the program. The first few bytes, we kind of know what they do already, so we're going to scroll down to main itself. Okay, so here's main. And the question is, on line 25, are we loading the correct constant into register A? According to this, the opcode itself is 6C, that's LDIA, and then the immediate value or the constant that we are loading into register A is 0B. Well, is that right? So the question is now answered by looking at line 28. On row 28, main 7 cont is defined as 11, and that is in base 10. So 11 in base 10 is in fact hexadecimal B, so dot 5 plus indeed is computing the correct return point from 7 to return to in main. So let me kind of wait a little bit, maybe a few seconds, to see if there are any questions about this part. No questions. Sounds good. All right, excellent. Okay, so now that we got that mystery out of the way, it also means that we do not need to use a label definition. We don't need a label definition anymore. So this label definition can now go, and now it becomes really just a matter of copy and paste. Every time you need to call you just copy and paste these four instructions and change 7, which is the label of the subroutine that you're calling. That's the only part that you have to change. All right, so with that done, we'll go ahead and implement the two functions that are super easy to implement first. Okay, there's a question. Yes, it will always be a .5 plus as long as LDI is after decrement. No, LDI has to be before decrement. If LDI is after, wait, yes, okay, you're correct. Nick is correct. So if LDI is after decrement, it is 5. If decrement is after LDI, it's going to be 6 because you have one extra byte for the decrement instruction in that case. All right, cool. So now we go to 5 and we'll go ahead and implement this subroutine, which is really just a copy and paste from the notes because we have 5 as the entry point of the subroutine. It has the same name as the C subroutine. And then we just specify LDI A5, which is the actual return value. And then we specify, oh, we have to get the return address. So we do LD. You cannot put it into register A anymore because register A now contains the return value. So at this point, I can only choose between register B or register C. They work kind of the same way. It doesn't matter which one you use, but you cannot use register A nor register D because register D is now the stack pointer. You cannot use register D for anything else. So we increment register D to deallocate the return address on the byte on the stack, and then we do a JMPB. That's how we implement 5. So 2 is going to be about the same. The only difference is what constant do we load into LDI. So we first name the subroutine, and then we just do a super lazy copy and paste, and then we change the 5 to a 2, and we're done. So do we have any questions about this part? How 5 as a subroutine is implemented and how 2 as a subroutine is implemented. Okay, no questions. Okay, if there are no questions, then we're going to take a look at 7. All right, so we know that 7 has to call 5 and 7 has to call 2. Okay, we know how to call, that's fine. So we say LD decrement D, allocate the space on the stack, LDI. We can use register A in this case because register A at this point is not used for anything else. So register A, B, or C, they can all be used at this point. Okay, so I would use register A dot 5 plus, which is the new thing that we have introduced today. And then we push it on the stack, which means it is a stda. We store the return address on the stack, and then we do a JMPI to 5. Okay, so when 5 is done, it's going to come back to whatever instruction is highlighted on this line. Okay, so now we can do another call. Okay, and because calling 2 is about the same, I'm just going to copy and paste and only change where we're going. So we put a 7 over here. Okay, so now we have called 5 and we have called 2. Sorry about that. This is recursive. We'll get to recursion at some point, just not right now. Okay, even possibly today, just not right now. Okay, so now we have two function calls. Okay, the first call is to 5 and the second call is to 2. And Nick is already thinking about where are we going to store register A, because at this point, okay, register A has the return value of calling 5. But register A is going to be overwritten by this at this point. In fact, it's going to be overwritten right here because we use register A again. Okay, then some people may say, well, why don't we use another register? Let's say we use register B, and then we avoid the problem of overwriting register A. Well, you have just delayed the inevitable for just a little bit longer, because by the time we get into subroutine 2, it is going to overwrite register A with a value of 2 over here. Okay, So Nick is saying in this case the function can use register B. Well, but we cannot because the convention between the caller and the callee. Oh, you're saying you cannot. Okay, so we cannot use register B because the convention is every single subroutine that returns a scalar is going to return the value through register A. Okay, so we have a little bit of a problem. Okay, but what about this solution? Okay, we still have register C floating around, right? So we can do a CPR, which is copy register, and copy register A to register C, and then when we get to this point, register A now has the return value of calling 2, which means, that's easy. I can just add register C to register A, and we are done. Okay. Okay, we got a question. Nick is gonna type his question. How do we know that C is free? Now, that is a very good question because a subroutine is free to use any register. So a subroutine can use register A. Well, in this case, register is mandatory because it is the return value register. But what about register B and register C? There's no guarantee that a subroutine will or will not use register B or C. You cannot assume, the caller cannot assume that a subroutine does not mess around with register B or register C. And Dom is asking, would it not be better to store the return value at places in RAM than load it in when we need to? Yes, but the question is, where do we want to store it in RAM? And I think Nick has the answer. There's one place in RAM that is very, very useful for stashing things away. The stack, exactly. So what we need to do is when register A still has the return value of 5, we push it on the stack. Okay, because anything that is pushed on the stack is stored. We may, overwrite register A, but the value that we have saved on the stack will still be there. So at this point, we say, let's go ahead and push it. Okay, so the CPR method is not going to work because there's no guarantee a subroutine will not use register C. So this approach does not work. Okay, what we need to do is to push A, register A, on the stack. Okay, so now we have to remember the sequence to push something on the stack, which we have already used several times in today's lecture because that's how we push the return address on the stack. This time we are pushing the return value on the stack. Okay, so make sure that we can differentiate between those two. One is the return address when we call, one is the return value, which is what we need to do right now because otherwise register A is going to be overwritten and we would have lost the return value of calling 5. So the sequence is to allocate first, okay, so you decrement D, and then you store to whatever D is pointing to after the decrement. So this is how we push register A on the stack, okay. So at this point, register A is already pushed on the stack, which means we can go ahead and mess up register A now, okay. In fact, let's do it right away. Yay! Because we don't need register A anymore. We can just overwrite it. So by the time we get back here from calling 2, we still have the return value of calling 5 sitting on the stack. Okay, now when something is sitting on the stack, it is in RAM, it is not in a particular register. So we can't really use it right away for adding to something. Okay, and someone's going to say, well, can't we do something like this? So we have to pop it into register first. That is correct. But I want to show a common mistake that people would use is to do something like this. Why can't we add whatever register D, which is the stack pointer pointing to, which is now the saved return value of calling 5, and just add it to A? because the mnemonic only adds two register. That is correct. So let me just emphasize why this is not going to work. Okay, we'll emphasize this is not going to work. Okay, we cannot dereference it. Yes, because the architecture itself has no way to dereference something and use it right away to put it into the ALU. Okay, so I'll go ahead and explain this in details. Okay, because I think it is really important to understand it. And Nick is also right that the parentheses, let me emphasize which parentheses we are talking about here. That is decorative. Okay, it's no more than a hood ornament saying that I'm driving a Mercedes. Okay, if you take that away, would the Mercedes still drive? Well, no better than before, but yes, it will still drive if it was drivable before. Okay, so that's basically, it's just syntactically, I want you to see that register D is being dereferenced in instructions where it would treat register D as a dereference register. But add cannot do it. Okay? But I will go into even more detail to show you why it cannot do it. The first thing we do is we go to the processor subfolder, and let me see if I can just pin it so that it doesn't reload all the time. So I go to auto tab discard and say keep this tab, do not discard it. Okay. So we go to the opcode table right here, and then we go to the add instruction. No, there's no mnemonic to add with a dereference value, and I'll explain why there is none like that. Okay, so we go to the add instruction. Okay, where's the add instruction? Right here. So row 26 explains the add instruction, and it clearly states that the add instruction will add register Y to register X. There's no dereferencing of any kind happening here. Okay, so then the next question is why? Why can't we introduce another opcode, another mnemonic that can add indirect to a particular register? To explain that, and there's and Nick is correct. There's no mnemonic to add with the reference value. But why is that? Okay, is it because TAC is too lazy to make an instruction like that, or is there actually a good reason for it? So now we are going to open a new tab so I can start up Logisim. And instead of typing the whole thing, I'm just going to look at something that is easy for me to. Oh, okay. 1915. There we go. All programmers are easy. Well, all the good ones anyway. Because the lazier the programmer, in other words, the less repetitive chore the programmer wants to do, the more the programmer wants to automate a program to do something. Okay, so we opened up the processor design. Okay. All right. So when you look at this particular design, okay, we ask the question, how come there's no dereference and add in the same instruction? Because it doesn't work. There's no way to do it. When you're dereferencing, what you're doing is you're using one register to specify the address port of RAM, and then you're taking the data port, which is now an output from the RAM component, and feed it somewhere. Okay, that is dereferencing. It's reading dereferenced. Okay, which is what we're attempting to do now. So now the question is there any way to feed the output of the D port of RAM directly into one of the two inputs of the ALU so that we can perform the add? And the answer is no. There's no path to do it. So we can use the data port to update several things. We can use it to update the instruction register, and that's what the fetch cycle is all about. We can use it to update the program counter even. Okay, this is how we can, let me see. Yeah, so we can update the program counter because we can implement a JMPI or J something I instruction, a conditional branch instruction. We can even use it to update one of the four registers in the register bank, which are called A, B, C, or D. but there's no way to feed it directly into the ALU. So that basically answers the question. Okay, the computer architecture itself does not support this type of operation. There's no way to take the output of RAM and put it into one of the two inputs of the ALU. Now, is it possible to change the computer architecture so that it can do that? The answer is yes. Okay, but that would mean the processor is no longer a RISC processor. Okay, and I think this is out the first time that we kind of really go in to talk about what is RISC versus what is Sisk. Okay, so we'll go ahead and look up what is Sisk and what is RISC. So Sisk versus RISC. Okay, Sisk stands for Complex Instruction Set Computer, and then RISC stands for Reduced Instruction Set Computer. So when I press the Enter key, okay, the first one is a fairly good explanation already. RISC stands for Reduced Instruction Set Computer, and Sisk stands for Complex Instruction Set Computer. So RISC basically means we are trying to minimize the amount of transistors on the processor. Basically that translates to minimizing the number of gates, the number of multiplexers, the number of demultiplexers, and so on. So now let's switch back to LogiSim. So if I want to turn this processor, so that if I want to modify this processor so that it can actually support indirect add, that means I have to complicate the design a little bit. I'm going to use up more transistors. I'm going to use up more gates. Because I need to use more gates, it's going to add more transistors to the processor design. So why is that a bad thing? Okay, because it seems like this is a good thing to have, because instead of having multiple instructions to do one thing, we have only one single instruction to do exactly the same thing. That is actually the reasoning behind people who support Sisk type of design. Is, hey, we can use one single complex instruction to replace a whole bunch of reduced instructions. Why not? Okay. So I want, this is a little bit hard for me to illustrate, but to keep you guys entertained, I will try my best. Okay. So we're gonna go gamer room, and we have a LAN party. Okay. So we're gonna pull up some pictures of that. Some of these pictures are actually pretty good. Okay, so we're gonna use this one here. Okay, so this is definitely a home setup with a lot of monitors and probably gaming computers. Okay, so we look at this and go like, so what does this have anything to do with RISC versus Sisk? Exactly. Um, so it has to do with the size of the processor, and also has to do with the heat produced. Okay. So Bo has the right idea. Okay, so Bo has the right idea uh, of something. This has to do with heat. Okay. Um, okay. So let's think about this a little bit. Okay. So let's say that you are playing League of Legends and you got four friends. So altogether, there you have five people in the same room, so that you guys can yell at each other and figure out who is at fault when somebody dies. Okay. And let's just say that you guys all have top of the line. Yes, LOL. Um, so let's just say that each one of you has top of the line, type of gaming computer, and you guys have relatively big monitors so that you can keep an eye on everything. Okay. So we are talking about 1 kilowatt per computer. That is true. Okay, so Hugh brings up a good point, but that's not even the key issue that we are encountering here. Okay, the key issue has to do with heat. So I'm going to switch back to mousepad. Okay, but probably not the same mousepad that I had, because that one still had code in it. So I'm going to open up a new window to illustrate my point. Okay, so you have 1 kilowatt per computer. And with the display, we'll just say that you're combining the display and the computer, and the graphics card and all the cool stuff, okay, all the LED lit headsets and whatnot, mice and whatnot, it's 1 kilowatt per computer. Okay, and we got 5 computers in the room. Okay, so what is the total thermal output of these computers? But hold on a second here. Okay, are we really sure that the all 1 kilowatt of a computer is actually turned into heat? Okay, doesn't processing actually take some energy? Isn't we aren't we using that energy to do computation and not generating heat? No, unfortunately, everything turns into heat. Okay, well, some turns into light. Okay, that has to do with all those fancy LED backlit, not backlit, but lit chassis and headsets and mice and stuff like that. But that's not taking a lot of power. Most of this is actually turning into heat. Yes, even those LEDs produce heat, but not entirely because LEDs are fairly efficient of producing visible light, which will hit the wall, hit something, and then it turns into heat again. Yes, all energy becomes heat. Yep, something about thermodynamics. That is actually correct. So now with 5 computers, we have 5 kilowatt of heat in the room. Now, what exactly is 5 kilowatts of heat? That's kind of like you're running two, three. It's running three hair dryers at high. Okay, on high. Okay, and you might think, well, but that doesn't seem too bad because I have used a hair dryer before and it doesn't seem to be too bad. Yes, but you were only using one hair dryer for maybe, depending on the length of your hair and how you want to do it, okay, you might be turning it on for what, 5 minutes, 10 minutes, 15 minutes at the most, okay? That's not really a whole lot of heat produced. If you have three hair dryers turned on high on for like a few hours, that's a lot of heat energy. And there's no way you can get rid of that heat fast enough with a normal house. Your air conditioner cannot keep up with that type of thermal output. Okay. All right. So that applies to I just skipped it. There we go. So that applies to a gamer setup. Okay, a LAN party. Okay. So what does that have to do with your Risk versus Sisk? So if you think you're pushing the envelope of getting rid of heat within a certain room because you want to pack as much processing power into that room as possible, what do you think of data centers? Okay, the data centers like from Google, from Facebook, from the government, and so on and so forth. Oh yeah, you can use it's in Sacramento in the winter um, with 5 kilowatts, output in a room that's about 12 foot by 12 foot. Um, Even if you open all the windows, you cannot get rid of the heat fast enough. People would actually die from heat exhaustion in the room. So, but with a data center, it becomes a real issue because Google doesn't want to build new data centers unnecessarily, and how much processing power it can pack into a data center turns out at this point it is not limited by how much hardware you can pack into the building. It has to do with how much heat you can extract out of the building. And as it turns out, RISC processors, even though each instruction doesn't do as much, the amount of energy to perform a particular operation is less than the amount of energy for a Cisc processor to do exactly the same thing. Okay, so let me give you an example. Let me switch back to mousepad here. Okay, so let's just say that you want to compute in games, especially 3D games. It is pretty common that you have to compute sine, cosine, and stuff like that. Okay, so let's just say that sine takes we use this calculation as a consideration. Okay, so we say sine. What is the sine of uh, 0.214? Okay, so we want to compute what is sine of 0.214. Okay, a RISC processor will uses less energy compared to a Cisc processor. Okay, that is the bottom line. Okay, because it has fewer transistors, so it doesn't generate as much heat. Now, you can say that, but it needs to exercise the transistors a little bit more than a Cisc processor. That is actually correct. But in a Cisc processor, a lot of transistors are just sitting there doing absolutely nothing for most instructions, because the Intel x86 processor, or I should say the 64-bit AMD instruction set, okay, they have hundreds of instructions. Okay, probably in the amount in the scale of 4 to 500 instructions. My toy processor only has, I think, 21, and not every single one is actually needed. Some are really convenience instructions, so it's not a pure RISC processor anymore, but it is a practical RISC processor. So in an Intel processor, because it needs to maintain backward compatibility, all of these transistors, we are talking about what, millions, or billions of transistors. A lot of these are really just sitting around doing nothing, just in case it is needed for backward compatibility. Okay, and that's why they are not energy efficient, because you're basically packing a lot of stuff, but it's not necessarily needed. One way to look at this is going for a camping trip. So you can go for a camping trip using just a backpack and a tent, just minimalist, okay? Or you can go camping, in an RV. Which one is more energy efficient? I mean, the RV literally includes the kitchen sink. Yes, the RV you can also do a refrigerator, and you can also have a stove and whatnot. But at the end of the day, in order to survive in the wilderness, in an RV is less energy efficient. Yes, so Bo is correct. If we do not need to maintain backward compatibility, processors would be a lot more efficient compared to what they are now. So if you look at the 64-bit version of the processor in a cell phone, which typically is an ARM-based processor, and you look at the 64-bit version of an Intel processor on a typical desktop computer, the amount of energy it takes to do a particular calculation, such as the sine of 0.214, the Intel processor takes significantly more energy compared to a RISC processor. So I guess the follow-up question to both question is, then why do we need to maintain backward compatibility? Now I know I'm kind of digressing a little bit from the main topic, but I think it is necessary for people to understand this, because this kind of stuff is usually not exposed in consumer electronics or technical description of consumer electronics. Um, what was I trying to say? I just lost track of my thinking. Let me think. Oh, backward compatibility. That's it. Okay. So backward compatibility is something that is kind of strange. Okay, because if you look at most distributions of Linux, okay, for instance, you can look into Debian, you can look into Ubuntu, but Debian is a good one to look into. Okay, so you can look into it and go like, how many architectures does it support? Okay, and we click on this supported hardware, and you have a fairly reasonable list of architectures. We all know about the x86, 32-bit of the x86 architecture. We also know of the 64-bit version of the Intel processor. So those things are like, okay, we know that. Okay, what about the ARM processor? With the ARM processor, it has the original ARM, which cannot perform floating point calculations in hardware. We have the ARM with an FPU. FPU stands for floating point unit, which basically means the double representation is natively understood by the processor hardware. And it can perform addition, subtraction, division, multiplication, and stuff like that really fast compared to an ARM that has no FPU support. And we also have a 64-bit version of ARM, which has a significantly larger address space. We have 32-bit MIPS processor, Big Endian, Little Endian, which is the 64-bit MIPS processor. For those of you who are going to transfer to Berkeley, you will come across the MIPS architecture again and again. When you after you transfer, because that's kind of an architecture that originates from Berkeley. And then we have the power system, or otherwise known as the power PC processor. And we also have the 64-bit IBM System 390, which is a mainframe type of computer processor. So the list is actually fairly good, even for a kind of stock, Debian distribution. So now the question is, well, it doesn't seem like we need backward compatibility because to rewrite the core part of a Linux kernel to support a new architecture is really not as much work as most people think it is. Okay, because Linux is mostly written in C and only a small percentage is written in assembly. You can look it up and find out what is the percentage. Okay, so let's go ahead and do that. Okay, so we'll say percentage of Linux in C. Okay, so it says right here, about 97% of the world's 500 most powerful computer runs Linux kernel. It just says it's mostly written in C, but it doesn't quite say the percentage. Okay. Okay, let's ask the question in a slightly different way. So how much of Linux is in C? Okay. Mm, or we can reverse the question and ask how much of it is written in assembly. It doesn't say. Or we can go to GitHub, yes. But I think the percentage is relatively low, which means to retarget Linux for a new architecture is not really that big of a task. Okay, I'll go to GitHub. All right. So um, if somebody finds out, just let the rest of the class know because I kind of want to continue with this discussion in a slightly different direction. So now the question is, why do we maintain backward compatibility? Is it Intel that is saying that we need to sell processors, so we need to maintain backward compatibility? Not quite. It's actually Microsoft, strong arming Intel. Yes, that would be the correct thing to do is to blame it on Microsoft because Microsoft says, we do not want to retarget our operating system because it takes too much work, and as a result, they tell the hardware manufacturers, do not lose that backward compatibility because if you do, we are not going to uh, support your processor, and then the processor manufacturer would lose uh, uh, profit. Oh, thank you, Nick, for looking it up. 1.2%, which is not a whole lot. I mean, I know Linux is a pretty big piece of program, but it is still not really that much. Okay, 1.2% is not that much. Okay. Oh, Eugene did. Thank you. So that really kind of puts everything into perspective because how come you do not have a 64-bit ARM processor in your Fitbit? Because well, if you did, you're going to be lugging a big battery for exercise purposes. I mean, just lugging that battery around is going to give you enough exercise. So that's kind of the bottom line. All right, so this is a big circle, going back to the original point that we were talking about, which is, oh, I just went over the screen that I want, which is this one. So this is a very minimalistic processor. It has, I'm pretty sure it's not as optimal as it possibly can be, but it is pretty darn optimal already. It's pretty small. Um, and there's just no pathway. Okay, there's just no pathway to go from the data port of RAM into one of the two inputs of the ALU. Okay, so that goes back to answer the question of why do we not have that instruction. So let me go back to the code here. So that answers the question of this does not exist. Okay, we cannot do this. Not because syntactically we cannot do it, but because the syntax is nothing more than declaration of the mnemonic that the assembler takes to translate the code. The real problem has to do with the processor itself because I want it to be as minimalistic as possible while still being practical. It doesn't have this. Okay, so we're going to comment out this instead of erasing it. I'm going to comment out it because now we have to say, well, if we cannot do this, what are we going to do? Well, somebody already answered the question earlier, of saying, well, we have to put it into register first. Okay, so now register B has the return value of calling 5, but register A still has the return value of calling 2. So now we have both values in registers. Add will now work properly because we just have to add B to A, so that A becomes the sum of the two. And once we have the result calculated, we can now return to the caller. So return to the caller. Oh, we are forgetting one thing, okay? Because once we have utilized the value that the stack point is pointing to, we have to deallocate it. So to deallocate that location on the stack is to increase the stack pointer. We are moving the bookmark up by 1 to basically say anything below the bookmark is now available or it is not in use. Okay, so once we have done this, we can now go ahead and retrieve the return address. The return address can no longer be retrieved into register A because register A is now used to specify the return value. So we can use register B or register C, increment D again, this time to deallocate that spot on the stack that was used to store the return address. And then we have a JMP instruction to register B in this case to go back to the caller. Okay, so this is a really long story to describe something that's relatively simple because I kind of digressed to talk about Sisk versus Risk, the trade-offs and why people do prefer Risk at this point. Okay, so we're going to do Control A, copy everything, and then we paste it into the assembler. Okay, go back to the assembler, and I probably want to pin this one so it doesn't reload. Here we go. Go back to the source tab and control delete first. Select one and then paste. Give it a few moments to resolve the labels. Okay. And I'm not seeing any errors, so that means we can go to the RAM file tab, download the CSV, and we'll download it as 7. 7.csv is the name of the program. Alright, so the next thing that we need to do is to run the program, but we don't want to run it inside in the GUI mode of Logisim. We can, okay, but we won't be able to see um, the calling and the returning if we just look at the GUI mode of Logisim. So I'm going to close Logisim and restart it, but using the command line only this time. Okay, um, so we'll go ahead and specify the same thing. Okay, and this time we have to also specify the processor. So it's in my documents folder under CISP310 processor 0003.circ. Then we specify dash tty table dash load, and the file name is 7.csv. I think that's all we need to specify, and then we redirect the output to log.tsv. So the log file is going to be analyzed by the trace analyzer. So now we go to the trace analyzer, and then we import the spreadsheet into here. There we go. Replace current sheet use tab and do not convert. And I see some people have already opened it so that they can actually look at the trace analyzer on their own screen and navigate to whichever part they want to look at. So I think that's a pretty smart idea to pre-open the file on your own. Another advantage of teaching this class using a cloud-based tool. And it's getting there. We just have to wait a little bit longer. There we go. All right, so the first thing we want to do is to check, did we end up with a 7 in register A? Okay, because when the program concludes, um, that's after we call 7, and we should have a return value stored in register A. All right. Okay, I just clicked it a little bit too soon, and okay, there's no easy way to use that scroll bar. Well, we can always do one thing. Okay, if we are confident the register A is going to get a value of 7, we can just look for that. So we can now go to edit and do a search. Okay, find and replace. And we're going to look for A equals to 07 because it's a 2-digit hexadecimal number. And we just need to find, none of these other options really is needed. So we just say find. And there we have it. And you might say, well, are we really sure this is the last time we update 7? Well, that's not, okay, because it is actually inside the subroutine of 7. So we still have to go continue a little bit because 7 has to return to main, and the main is the one that has the halt instruction. So we still have to go a little bit further. Okay, keep going. All right, the browser is thinking this is taking too long. There we go. Okay, so it's still working, and this is the halt instruction is at location 22 in hexadecimal, and we can double check that too. So we can actually go to the assembler and go to the assemble tab and scroll down to main and look at the halt instruction and see where the halt instruction is located. So the halt instruction is here. It is located at location 41 in decimal or 229 in hexadecimal. So when we go to the trace, it is only stopping at location 22. Hmm. And there's nothing after that. If I oh no, there's more. Okay, so when d gets back to 0, that's the increment inside 7. Okay, the increment d inside 7 is the reason why d is incremented back to 0, which is at location 21. So now we can go back and check. Okay, is location 21 really the increment d, the last increment d instruction inside 7? So we go back to the assembler and we look at increment d, which is, I think it's this one. Okay, let me double check. Yep, so all of this stuff here is inside 7. So the last increment D instruction is row 47 in the assembler, and it does have a location of 21 in hexadecimal. So this is the kind of stuff that I want you guys to do, is to question. It's like, okay, who changed the stack pointer last so that it is now balanced again, because D was 0 to begin with. Now we got back to 0. So I want you guys to start to ask questions about this, start to ask this kind of question and be able to answer the question by looking at the trace and also by looking into the assembler window. Um, because to me, that is the best way to learn about the material for this class, is to try to figure out why is it doing this, or which instruction is doing this, and so on. So let me just kind of pause a little bit and see if people have any questions at this point. No questions? All right. And let me double check and make sure my stream is still going, because there was one time the stream died and I just thought, hey, the whole class understood all the concepts, I can just move on. Nope, no, Discord just stopped streaming, that's why. Okay, but this time nobody has any questions. All right. So now we go back to the course. Okay, we got a question. Okay, we are definitely streaming. Okay, thank you. Thanks for confirming. All right, so that basically finished this particular module, which is how we return a scalar. Okay, so now we move on to something that's a little bit more sticky, but not too much more, which is what about parameters and local variables? What about those concepts in C and C++? Can we do all of those things in a program that is written in assembly language? So let's go ahead and make a new program first. Okay, so we'll go ahead and make a new program, and we'll say new window. Okay, so here's a new one. And this time we want to look at something that has parameters. Use the stack. Very good, Nick. Isn't this class boring? Everything is all about using the stack. It's always about the stack. It's always about the stack. All right. So we're gonna use the add. It's like playing magic. All right. So we're gonna use this as an example. Okay. We're gonna have implement a subroutine. All it does is to add the two parameters that are passed to it. Okay. And main in this case is we're not going to make this super fancy. All we are going to do is to say, let's just call add with 2 and 5 as its parameters. So we're going to get back to 7 again, but using a different way to get to it, okay? And return 0. This is our program to implement now, okay? So the question is, how do we do this? How do we pass parameters to a subroutine? So we got a few obvious choices. Okay, so let's rule out the ones that do not work. The first obvious choice is what about registers? Okay, we got 4 registers. Can't we use that to pass information from the caller into the subroutine? The answer is yes, we can. In fact, some compilers, someone should program something that takes C code and compiles it into assembly language we use. I'll pay. I think that's GCC. You should pay someone to retarget GCC to generate code for the TTP. But it's it may be difficult for someone to take on that job. That's one of the reasons why I stopped using the x86 architecture, because some people are starting to use the compiler to do their work. All right, so getting back to this program, let's see how we can do this. So the problem with registers is we only got 4. Okay, one is already used just as the stack pointer. We cannot use it for anything else. So we only got 3 registers left. For the other 3 registers, sometimes we would like to have registers around just so that we can do computation. If the registers are also used for um, passing information into a subroutine, then we don't have any registers left to actually do any sort of computations. So that kind of doesn't work. Okay. The second one is how about allocating some static area in RAM and just use those areas so that we just have to make sure that the caller and the callee agree that this area here is used for this parameter, this area here is used for that parameter, and so on. That approach actually worked. Okay, there were programming languages like that. COBOL is one, and then Fortran is the other one. Okay, both of those languages have what we call linkage areas, which are statically allocated areas, so that a subroutine knows, okay, I would go to these places to look for my parameters, but they're static. Okay, the biggest problem with this approach, it's twofolded. The first problem with this approach is you cannot have recursion, because if you want recursion, then every invocation of the subroutine needs its own space for parameters and also local variables. And having a statically allocated area means that you cannot do that. Okay, so that's the first problem. And then some people will say, but every single recursive algorithm can also be rewritten so that it is non-recursive, so that it is just iterative. That is actually true. Okay, we can get rid of recursion altogether because there are ways to translate every single recursive algorithm so that it is no longer recursive. So what is the big problem then? Well, it has to do with multi-threading. Because if a subroutine has a statically allocated area for local variables and also parameters, then multi-threading cannot work. The problem with multi-threading in this case is because multiple threads inside the same process, they share the same data space. The only thing they do not share, guess what? Okay, because this is the boring part of this class. The only part that threads inside the same process do not share are their stacks. If you have a process, which is basically a program in execution, and it has 5 different threads, the 5 threads, each one has its own stack. Okay, so that is the other issue. Okay, because if we use a statically allocated area, the multi-threading is not going to work. So how are we going to solve this problem? How do we pass information from the caller to the called subroutine? We use the stack. Okay, that's what we're going to do. So the best way to illustrate how that works is really just to code it, and then I'll show you how that works. So we'll go ahead and do a search and replace and see if this can deal with um, regular expression. No, it cannot do regular expression. Okay. That's okay. It's not too big of a deal. We can do it just a few lines at a time. All right. So main needs its own entry point label. Okay. No big deal. Now we need to implement add. So since it has to do with stack, that means it has to translate into one of the most primitive operations of a stack, pushing or popping. Pushing is for putting things onto the stack, so this is what we need to do now. So the next question is, well, should we push 5 first or should we push 2 first? Because it would seem to make sense to push 2 first, because 2, after all, is the first parameter. But the convention used by C and C++ is we push the last parameter first. Okay, in other words, in this case, we push 5 first. 5 is known as parameter y from the callee's perspective. Okay, because we have to pop in the other order, sort of. Okay, the reason why this makes sense is because the first parameter actually has an address that is lower than the second parameter, and it also supports the dot 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 notation. That's basically the reason. Last in, first out. Yep. So we have to push 5 first. Okay, so to push 5, we LDI A5, and then we decrement the stack pointer. In this case, whether you do it doesn't matter which order you do it. Okay, so now we have pushed 5 on the stack. Then we push 2 on the stack. So now we do exactly the same thing, except A is loaded with the constant of 2, and then we push that on the stack. So we push 2 on the stack. Now we call the subroutine, which means now we have to uh, decrement D first. This one, we do want to make sure the order is right. And then load A with .5 plus, which is the return address. Store that on the stack. Push the return address. Now we can continue execution in the subroutine. That's a simple JMP-I instruction to add. Okay, and then we'll put a question mark here to do. What do we need to do over here? The next instruction is going to be a halt instruction to replace the return. Yep, we have to do the halt, but there's something before halt that we should do. Um, but I'm not going to tell you guys what. Okay, when we trace the subroutine, then we'll actually see, wait, hold on a second here. Why is that? Okay, so until that time, we'll go ahead and implement the add subroutine. Okay, so entry point has its own label, which is the same name as the subroutine itself. Get rid of this, and also get rid of that. All right. So the first question is, where do we find x and where do we find y? Um, because they're not in registers. Okay. So how do we find these items? So in order to understand this part, we want to understand what exactly is on the stack. Okay, so I'm going to attempt to use text to represent the result or what is on the stack. So when you look at this, the top of the stack is on the, okay, I have to kind of think of a way that makes sense. So the top of the stack is on the left hand side, and then the portion of the stack that is already in use is on the right hand side. Okay, and I'll put a square bracket around what the stack pointer is really actually pointing to. Addresses of function and function parameters are stored on the stack. Yes, that is correct. But we want to know, well, not the address of functions, it is the return address of calling a subroutine that is stored on the stack. The address of a function is not necessarily stored on the stack unless you want to call a subroutine passing the address of a function, okay, which we are not going to touch for now. So when we push the 2, what is going to happen is 2 is now being pointed to by the stack pointer. The stack pointer always points to the last thing that we push on the stack. But 5 is still on the stack, so the stack looks like this at this point. We have 5 on the stack, which has a higher address, and then 2 is at a lower address, but the stack pointer is pointing at the 2. Then we push the return address, which means at this point we have the return address on the stack, but the 2 and the 5 are still on the stack. In fact, the 2 is 1 byte after the return address, and then the 5 is 1 byte after the 2. So are we still doing okay with this kind of picture, kind of showing what is on the stack at the time that we continue execution in add? Okay, makes sense. Okay, anyone else? Any questions? Okay, go ahead, Angel. Go ahead and ask. Okay, the question is, if we want to access multiple functions or parameters, we memorize the address on the stack and call it later. No. The answer is we do not. Okay, so LDI comma dot 5 plus is loading A with the return address. That was explained a little bit earlier. Yes, so dot 5 plus means 5 bytes after the start address of the current instruction, the instruction where the dot on the same line as the dot. Okay. Any other questions? All right. So I'm going to emphasize it is really important to ask questions when I talk about the concept, because when we ask questions about concepts a little bit later, um, it's not as effective when I try to answer those questions. All right, so getting back to this routine, at the entry point of add, this is what the stack looks like. Okay, we got the return address, and then we have parameter x, and then we have parameter y. From the perspective of the called subroutine, we are not going to say this is 2, we're not going to say this is 5, because the subroutine can be called from different places, and different callers will push different arguments on the stack. So we can only refer to these two as parameter x and parameter y. And the return address is in square bracket because that's how I represent that this is actually being pointed to by the stack pointer. So now we want to get to x and y, and then we add those two, put the sum into register A, and then call it good. Okay, that's the whole purpose. I'm looking at the time, we are at 48, okay? But since we don't have to transition to the lab, right? So we got an extra 10 minutes to talk about stuff. Cool. All right. So what we'll do is we're gonna use a CPR instruction, and we copy register D to register C. So at this point, I need to kind of keep track of which register has what, okay, on the stack. That's one way to do it. I'm going to do it the other way. Sorry about this. I'm taking this back, okay. Instead, I will define some labels, okay. I'm going to define some labels. The first one is return address is defined to be 0, x is defined to be 1, y is defined to be 2. You go like, but x is not 1, y is not 2. Well, what x and y are really defining is the number of bytes from where d points to parameter x. In other words, y is kind of the same way. Okay, so what these labels are defining is we know where the stack point is pointing to. So how many bytes are these items away from where the stack pointer is pointing to? X is 1 byte away or 1 byte after where the stack pointer is pointing to, and Y is 2 bytes after where the stack pointer is pointing to. So that's what these labels are for. Okay. So once we have these labels done, then we can do something like this. We can do LDIA with X. So that literally is just loading 1 into register A. Okay, so we can say A equals to 1 as, as the result of this operation. That's not going to do us any good until we do this. Aha! So what is this going to do? This is basically saying A is now 1 plus whatever register D has. But what is exactly 1 byte after where register D is pointing to? It is the address of X, not X, but it is the address of X. Yes, so Angel is correct that we need to be mindful of what items are on the stack and where they are relative to where the stack pointer points to. Okay, so uh, Angel is absolutely correct about that. Okay, but do we want to add the address of X to the address of Y, or do we want to actually add X to Y? Well, we want X and Y, so getting to the address of X is good because it will lead us to X itself. So we need to do a LDAA so that now A is the dereference of the address of X, which guess what? It's just X itself. We now have the value of parameter X in register A. Register B can do the same thing with Y, so we load B with Y, which literally is just saying that register B is now 2. We now add BD, so now B is 2 plus register D, which is the address of Y, because that's where we can find parameter Y is 2 bytes after where the stack pointer points to. The address of Y is useful, but that's not the final result that I want, so I'm going to do LDBB. So now the B is the dereference of the address of Y, but when you dereference the address of something, you just get that something back. Okay? So at this point, we have register A being the value of parameter X. We have register B being the value of parameter Y. We just have to add those two. So we say add AB because the result has to be returned through register A. So add AB will kind of give us both the sum and store into the register the correct register at the same time. So that's how we are going to do this. And then we can now retrieve the return address, which is exactly where the stack point is pointing to. How do we know that? It's because of this. Okay, so we know that the stack pointer has been pointing to the return address on the stack this whole time. Okay, so we just say LDBD this time. So B is now the return address. Increment D to deallocate the return address, and then the JMPB to go back to the caller wherever we came from, and we're done. Okay, so this is main. That's the subroutine. So I think we are ready to run this program. So let's go ahead and give it a try. Control C, Control A, Switch back to the browser. Okay, there's a question. We then need to deallocate the space. That is correct. But let me illustrate what happens when we do not deallocate that space. So let's go back here, go to the source tab, delete, paste, go to the RAM file tab. It's still working. Nope. How come I'm not seeing anything? Oh, okay, wrong rows. Nope. Did I paste into the wrong column? Yeah, I pasted into the line 40 something. So the code is still there, it's just displays all the way to the bottom. That's okay, because we just have to scroll down to find it. It's still there. So we can still go to File, Download as CSV, save the file as 7 again. Yeah, I know I'm working a little bit over time, but I think it's really important to keep this momentum going because it will take a long time to restart this context. Then we switch back to the command line. Just rerun this program because I put it into the same file name. Okay. And then we switch back to the trace analyzer so that we can reload the trace, which is the log of the execution of this program. So we go to import, upload, log.tsv, and replace current sheet, specify tab, and do not convert. And don't tell me I forgot. Oh, okay. I know I forgot something important because that doesn't look right. I think I forgot two things at least. I forgot to do a jump so that it starts executing at the add instruction, at the add subroutine. I need a no op to begin the whole thing, and then jmp to main to start the entire program. I forgot about that. Alright, so let's do it one more time. Go to the RAM file. Alright, so let's switch back here, run the code again, switch back to the trace analyzer, and then re-import everything. So we go to import. There we go. That looks a lot better. Alright, so we can go to analysis and wait a little bit. Alright, almost there. Okay, so we got everything. So let me page up. There we go. And Nick was absolutely correct. The last update to the stack pointer was to change it back to FE, but not all the way back to 00, 0. So what this means is, as far as the stack is concerned, by the time we get to the halt instruction, the 2 bytes used by the 2 parameters are still on the stack. Okay, so if I switch back to the code, okay, what I'm saying is, at this point, we still have the 2 bytes for the parameters on the stack. So yes, so we not only are we leaking memory, but if main is a normal subroutine and it has to return to its own caller, the stack pointer is now pointing to the wrong place on the stack. It is not pointing to the return address of the subroutine. Now, main is special because it really does not have a return address, so it doesn't have that issue. But if it did, it would have that issue. So it is really important for us to remember to increment the stack pointer to deallocate the parameters. It is the responsibility of the caller to deallocate the space that is used for pushing arguments. Okay, I'm not going to rerun this program anymore because we probably would understand that, oh, okay, by doing these two increment D instructions, by the time we get to the halt instruction, the stack pointer would be 0 and it would be balanced. Okay, so I'm not going to do that part. But we do want to make a few observations. One is register A did end up with a 7. Okay, so that's kind of cool. If we are not popping our stack, can we check if the stack is empty or not? Um, hmm. The stack is empty when the stack pointer is 0 in our case. So yes, you can sort of check whether the stack is empty, but it really should not be something that you have to do because from the subroutine's perspective, you want to from the subroutine perspective, you need to count on the caller to have passed the arguments on the stack. So what I do want to show, okay, there's one more question here. In main, can we push the return address before pushing 2 and 5 on the stack? No, that cannot happen because because that's not the agreement between the caller and the callee. So the agreement between the caller and the callee is we push all the arguments first and then we push the return address. And that standard or that agreement is actually common to most implementations of C and C++. Okay, David is typing a little bit more. Okay, and because of that agreement, we can use x and y parameters in add. That is correct. So everything that we talked about today regarding calling, regarding the caller and the callee, it really has to do with the agreement between the caller and the callee. Where do we find the return address? Where do we find the parameters? That is all, it's all an agreement, between the caller and the callee. When a compiler is doing this, obviously it's not an issue, but when we are doing it, we have to make sure that we observe those standards. Um, just one more thing that I want you guys to observe, from this program. It has to do with what we actually push on the stack. What does it look like? Okay, so we have to look into column C for that. So when you look up column C, the first thing we push on the stack is a 5, which is parameter y. And then the second thing we push on the stack is at location FE, and that's our 2. This is our first argument. And then we have the return address pushed on the stack at location FD. Now, how do we know this is the return address? We can go to the assembler, go to the assemble tab, and go to the main subroutine. Okay, this is my fault that I kind of skip a bunch of lines, but functionally it's still here. So after we call add, or after we continue execution in add, we want to return to this instruction, which is the halt instruction, because this is before we inserted the two increment D instruction. And you can see the address of the halt instruction is in fact 1D. So when you look at the trace analyzer, this 1D is in fact the correct return address and is pushed on the stack at location FD. So when you combine these three push operations, then you can see that the return address is at the lowest address where the stack point is pointing to, and then the first parameter is next, and then the second parameter is 1 byte on top of that. So this is all kind of important stuff. Okay, and I know that I'm running out of time. I have been running out of time for 13 minutes, but it's really kind of important for me to finish at least up to this point. So do we have any questions before I turn off the recorder? No questions? Oh, okay. Alex has a question. Yes, somebody mentioned exam 2. Exam 2 is supposed to happen in somewhere in around week 11 or week 12. So I think this is week 9-ish, right now. So we have about maybe a week and a half to go before we need to look into exam 2. Okay, you're welcome. Any other questions before I turn off streaming, live streaming? No other questions? Oh, there's one more thing I almost forgot. Okay, I forgot to turn on the lab for tonight. How can I forget that? Duh. Okay, so before I turn that on, I do want to point out that there is a caller-callee agreement as a kind of really short document, but it summarizes all the things that the caller and the callee agree on. So you might want to kind of refer to that page from time to time. And the lab for tonight is parameters and return values, which are exactly the same thing that we just talked about. Is that a coincidence? Okay, so we go in, and the passcode is frame, FRAME. Definitely a coincidence, yes. But the access code is frame, and the due date is 1 week from today. And 1 week from today is the 31st. There we go. And I'll make the due date and I'll make the time 5:30 p.m. There we go. And then we save and publish. And now you guys have the homework assignment or the lab. Eugene is typing. What is the passcode for the previous lab? I can look it up.
Last in, first out. LIFO.
Oh, thank you. All right. Cool. Angel has another question. My stream just cut out. What is the code for tonight? It's frame. FRAME. There we go. Okay. So any other question? I think that should answer everything. All right. So if there are no other questions, I'm going to turn off live streaming. So I'm going to turn that off from Discord, and then I also turn it off from YouTube. But I'll stay online for to answer any additional questions. I might turn off the mic, but I'll be on Discord.